Hello there, and welcome to Mysteries Beneath Earth. Tonight, we are going to look up, past the clouds, past the atmosphere, to the one object in the night sky that feels like a constant companion. It hangs there, glowing in the silence, sometimes a slender crescent, sometimes a full, luminous coin watching over the sleeping world. We call it the moon. It governs our tides, lights our paths, and has served as the keeper of calendars for as long as humans have looked upward. To us, it seems frozen in a perfect, eternal dance with the earth. It feels permanent. It feels close. But tonight, I want you to sit with a thought that unsettles that sense of permanence. What if I told you that this companion is leaving us? It is not happening with a roar or an explosion. It is happening with a silence so profound that, for most of human history, we had no idea it was occurring at all. But it is happening. With every breath you take, with every tide that washes onto a sandy beach, the moon is inching away. It is a departure so slow that it defies our perception, yet so relentless that it determines the fate of our planet's distant future. Let's begin this journey not in the sky, but on the ground, in the high desert of West Texas. There is a place here called the McDonald Observatory. On clear nights, when the air is thin and steady, astronomers fire a pulse of laser light directly at the moon. It's not a weapon, it's a question. The beam travels through the vacuum of space, crossing nearly 240,000 miles in just over a second. It strikes a specific point on the lunar surface, bounces off a small, suitcase-sized device, and returns to Earth, where it is caught by a telescope. This device is not natural. It was placed there by human hands. On July 21, 1969, just moments before Neil Armstrong and Buzz Aldrin climbed back into the lunar module to leave the Sea of Tranquility, they deployed an experiment known as the Laser Ranging Retroreflector. It looks simple, a panel studded with 100 fused silica corner cubes, designed to reflect light back exactly in the direction it came from. Other missions, Apollo 14 and 15, and the Soviet Lunokhod rovers, left similar mirrors. For over 50 years, these silent sentinels have been sitting in the gray dust, waiting for flashes of light from Earth. By measuring the time it takes for that laser pulse to make the round trip. A measurement precise to within a trillionth of a second, scientists have discovered something profound. The moon is not staying put. It is spiraling outward. Specifically, it is drifting away from Earth at a rate of approximately 3.8 centimeters per year. Now, 3.8 centimeters might not sound like much. It is roughly the width of 2 fingers, or the rate at which your fingernails grow. If you stood on a mountain and moved 3.8 centimeters, you wouldn't feel the difference. In the span of a human life, the moon moves away only about 2.5 to 3 meters, the length of a small car. It seems negligible. It seems like a rounding error in the vast mathematics of the cosmos. But here, in the quiet consideration of deep time, there are no small numbers. When you multiply 3.8 centimeters by millions of years, the geometry of our world begins to unravel. This number, 3.8 centimeters, is the echo of a gravitational conversation that has been going on for 4.5 billion years. It is a conversation about energy, about water, and about the rotation of the Earth itself. It tells us that the moon we see tonight is not the moon of the past, and it is certainly not the moon of the future. Imagine looking up at the sky 100 million years ago. The dinosaurs roaming the Cretaceous plains saw a moon that looked very much like ours, perhaps just a fraction larger, a tiny bit brighter. But go back further. Go back to when the first tetrapods dragged themselves out of the swampy oceans. Go back to when the Earth was a water world, void of continents as we know them. The moon was there, but it was closer, looming larger, its pull stronger. The history of the Earth is, in many ways, the history of this departure. But why is it leaving? What force is pushing it away? The answer lies not in the moon itself, but in the Earth, specifically in our oceans. As the Earth spins, the moon's gravity pulls on our water, creating the tides. But because the Earth rotates faster than the moon orbits, the tidal bulge of the ocean is dragged ahead of the moon. This misalignment creates a gravitational leash. The Earth, in its rapid spin, tries to drag the moon forward, adding energy to its orbit. And in orbital mechanics, when you add energy to an orbiting body, it doesn't go faster. It moves higher. It moves away. It is a cosmic trade-off, a transaction of momentum. The Earth is giving up its rotational energy, slowing down very slowly, and giving that energy to the moon, pushing it into a higher, wider orbit. We are pushing away our closest companion with the very rotation that defines our days. This realization transforms the night sky from a static painting into a slow-motion explosion. The moon is not floating, it is fleeing, and this flight has consequences for everything. The length of our day, the stability of our seasons, the behavior of our oceans, and perhaps the very existence of life as we know it. Tonight, we will follow this invisible departure. We will travel back to the violent beginning, when the moon was a terrifying giant in the sky. We will walk through the geological eras where the days were short and the tides were tsunamis. We will look forward to the distant future, to a time when the total solar eclipse, the most beautiful coincidence in the solar system, will become impossible. And we will ask the ultimate question: what happens if the bond breaks? The 3.8 centimeters measured by the lasers in Texas are more than just data. They are a ticking clock. They remind us that gravity is patient. It doesn't need to hurry. It works on timescales that turn mountains to sand and oceans to vapor. The drift of the moon is a reminder that stability is an illusion created by our short lives. The universe is in constant motion, constant change, and even the ground beneath our feet and the satellite above our heads are part of a long, slow goodbye. As you listen to this, maybe you can see the moon from your window. Maybe it's hidden behind clouds, but it's there pulling on the Earth, and the Earth is pushing back, whispering to it to go just a little bit further, just a little bit farther into the dark. This is the story of that journey. It is a story of violence, of water, of time, and of the inevitable loneliness of a planet losing its partner. So settle in. Let your breathing slow down to match the rhythm of the tides. We are going to drift back through the eons to catch the moon before it slips away. The laser pulse returns to the observatory. The computer registers the photon. The distance has grown since yesterday by a fraction of a hair's width. The data is stored, a new point on a graph that stretches back to 1969, and theoretically back to the birth of the solar system. To understand where the moon is going, we first have to understand where it came from. Because the moon didn't just appear in this orbit. It wasn't captured quietly like a stray asteroid. Its birth was an event of apocalyptic violence, a collision that nearly destroyed the Earth before it had even barely begun. And in that beginning, the moon wasn't a distant lantern. It was a monster. Let's turn the clock back. Not just thousands of years, but billions, 4.5 billion years to be precise. to a time before the 3.8 centimeter drift had created the gap we see today, to a time when the Earth and the Moon were so close they could almost touch. If you enjoy exploring these deep stretches of time and the quiet mechanics of our universe, I'd be grateful if you liked this video and subscribe to Mysteries Beneath Earth. It helps us keep these stories alive, drifting through the algorithm just as the moon drifts through the night. Now, let's go back to the fire. To understand the drift, we must first understand the intimacy of the beginning. The distance between the Earth and the Moon today averages about 384,400 kilometers. It is a distance so vast that you could fit every other planet in the solar system. Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune, snugly into the gap between us and our satellite. It feels like a safe distance, a respectful distance. But it wasn't always this way. The moon was born in fire, and in its infancy it was uncomfortably, terrifyingly close. The leading theory of the moon's origin is known as the giant impact hypothesis. It suggests that around 4.5 billion years ago, when the Earth was still a protoplanet, a molten ball of magma cooling in the vacuum, it was not alone in its orbit. It had a stalker, a Mars-sized planetoid, which scientists have named Theia, after the Titan in Greek mythology who gave birth to the moon goddess Selene, was on a collision course. This wasn't a glancing blow. It was a cataclysm. Theia slammed into the young Earth with a force that defies human comprehension. The energy released would have been enough to vaporize Earth's oceans if they existed, and to melt the planet's crust entirely. The core of Theia likely sank and merged with Earth's core, enriching our planet with heavy metals. But the mantle of Theia, along with a massive chunk of Earth's own outer layers, was blasted into space. For a brief, hellish window of time, Earth had a ring, a disk of superheated rock, dust, and vapor swirling around the equator, glowing red-hot. It would have looked like Saturn, but made of fire instead of ice. And from this chaotic debris field, gravity began to do its work. Clumps of rock collided and stuck together. Accretion accelerated. In a time frame that some modern simulations suggest could have been as short as a few hours or months, this debris coalesced into a single spherical body. The moon was born. But this newborn moon was not the polite white disk we know. It was a molten ember, glowing angry red in the night. And most importantly, it was close, shockingly close. Computer models suggest that when the moon first formed, it may have been only 15,000 to 20,000 miles away from Earth. Compare that to the 240,000 miles today. It was roughly 15 to 20 times closer than it is now. Imagine standing on the cooling crust of the Hadean Earth. The sky is not blue. It is a hazy, toxic mix of carbon dioxide, methane, and volcanic ash. And dominating that sky is the moon. It would span nearly 10 to 15 degrees of the sky, huge, imposing, covering a vast swath of the heavens. You would be able to see the glowing lava lakes on its surface with your naked eye. You wouldn't just see it. You would feel it. At that distance, the laws of gravity were tyrannical. The tidal forces, the stretching power of gravity, scale with the cube of the distance. That means if the moon is 10 times closer, the tides are not 10 times stronger. They are 1,000 times stronger. But in the Hadean Eon, there were likely no oceans yet, at least not liquid ones. The surface of the Earth was a thin skin of rock floating on a mantle of magma. The moon's gravity would have raised tides not of water, but of molten rock. As the moon raced across the sky, a wave of magma, kilometers high, would have bulged up beneath it, flexing the Earth's crust, cracking it, releasing torrents of volcanic gas. The Earth was being kneaded like dough by this nearby giant. And the speed, everything was happening fast. Because of the conservation of angular momentum, the same law that pushes the moon away today, the early Earth had to be spinning incredibly fast. A day on the early Earth lasted only about 4 to 6 hours. The sun would rise, race across the sky in 2 hours, and set. 2 hours later, it would rise again. The moon, meanwhile, was orbiting the Earth much faster than it does today, perhaps completing a circuit every 10 hours or so. It was a chaotic, dizzying world. A planet spinning so fast it bulged at the equator, whipped by hurricane-force winds in a thick atmosphere, under the glare of a red, giant moon that raised mountains of lava with every pass. This is where the journey of the 3.8 centimeters begins. It begins in this gravitational lockstep. The interaction between the fast-spinning Earth and the nearby moon immediately began to change both of them. That massive tidal bulge, whether of magma or, later, of the first primitive oceans, did not sit directly under the moon. Because Earth spun so fast, once every 4 hours, it dragged the bulge ahead of the moon. Imagine the moon trying to pull that bulge back into line. It exerts a drag on the Earth. It's like a brake pad rubbing against a spinning wheel. Friction. The magma and later the water rubbed against the solid crust, generating heat and slowing the rotation that in those early millions of years. The recession of the moon was not 3.8 centimeters a year. It was likely much, much faster. The moon was being flung outward by the sheer energy of Earth's rapid spin. It retreated from the danger zone rapidly, spiraling out to a safer distance where the tidal forces were less destructive. By the time the Earth cooled enough for liquid water to pool into the first oceans, the moon had already moved significantly, but it was still far closer than today. The first oceans experienced tides that would be unimaginable to us. We are used to tides that rise and fall a few meters. In the Hadean Eon, the tides might have been 1,000 feet high. Imagine a wall of water, a tsunami that arrives not once in a century, but every few hours, scouring the barren continents, stripping away rock, and pulling minerals into the sea. These were violent, scouring tides that mixed the chemical soup of the early Earth. Some scientists speculate that this violent proximity was essential for life. The massive tides would have created vast intertidal zones, areas that were wet, then dry, then wet again over and over rapidly. This cycle of wetting and drying is known to be a powerful catalyst for chemistry. It concentrates molecules, encourages polymerization, and might have been the crucible where the first RNA strands began to weave themselves together. So, in a strange twist of fate, the very violence of the early moon, the terrifying closeness that raised magma tides and 1,000-foot waves, might have been the spark that allowed us to exist. We are children of the drift. If the moon had not been so close, the chemical mixing might not have happened. If it had stayed that close, the planet might have remained too volatile for complex life. The drift is not just a separation. It is a maturation. As the moon moved away, the Earth calmed down. The day lengthened from 4 hours to 6, then to 8, then to 10. The magma hardened. The skies cleared. The moon shrank in the sky from a terrifying overlord to a watchful guardian. But the mechanism never stopped. The water still bulges. The friction still grinds. The energy is still transferring, minute by minute, eon by eon. The moon is still fleeing the scene of the accident. To understand exactly how this works, why a spinning planet pushes a moon away, we need to look at the invisible machinery of gravity and water. We need to look at the oceans not just as habitats, but as heavy, shifting weights that throw the Earth off balance. In the next part, we will dive into the mechanics of this planetary break. We will see how the water in your local harbor is part of a global engine that is physically pushing the moon higher into the darkness. It is a story of angular momentum, a law of physics so strict that even planets must obey it. The violence of the birth is over. Now, the long, slow grind of the recession begins. We often think of gravity as a simple force. An apple falls from a tree. Planet orbits a star. Feels like a clean, invisible tether. But in the messy reality of a planet covered in water, gravity is not clean. It is grinding. It is heavy. And it is this heaviness that is driving the moon away. To understand the mechanics of the drift, we have to stop looking at the Earth as a solid rock. We have to see it as it really is, a spinning sphere sloshing with liquid. The oceans are not merely a blue veneer on the surface. They are massive, shifting weights. Millions of gigatons of water, constantly moving, constantly reacting to the pull of the moon. Here is the mechanism of the departure, the engine of the drift. It is a dance of timing and friction. As the Earth spins on its axis, it completes one rotation every 24 hours. But the moon is much slower. It takes about 27.3 days to complete one orbit around us. This difference in speed is the key. The Earth is spinning much faster than the moon is moving. Now, imagine the moon's gravity reaching down and grabbing the Earth's oceans. It pulls the water towards it, creating a high tide, a bulge of water directly underneath the moon. If the Earth were stationary, that bulge would sit perfectly aligned with the satellite. But the Earth is not stationary. It is spinning rapidly towards the east. Because the Earth is spinning so fast, friction drags the ocean floor against the water. The Earth, in its hurry, physically drags the tidal bulge forward, pulling it ahead of the moon. The high tide doesn't sit directly under the moon. It sits slightly ahead of it, leading the dance. This misalignment creates a gravitational imbalance. That massive bulge of water, extra mass, extra gravity, is now in front of the moon. It pulls on the moon, yanking it forward along its orbital path. In the laws of orbital mechanics, this is where the magic happens. When you apply force to an object in orbit, when you pull it forward to make it go faster, it doesn't actually speed up in the way a car does on a highway. Instead, that extra energy lifts it. It pushes the object into a higher, larger orbit. By dragging the tidal bulge ahead, the Earth is feeding energy to the moon, acting like a gravitational slingshot that very gently, very slowly, boosts the moon higher into the sky. This is why the moon is drifting away. The Earth is literally flinging it outward with the momentum of its own oceans. But nature demands a payment for this energy. The universe operates on a strict accounting system known as the conservation of angular momentum. Energy cannot be created or destroyed. It can only be transferred. If the moon is gaining energy to climb higher, that energy has to come from somewhere. Comes from US.AS, the tidal bulge pulls the moon forward. The moon pulls back on the bulge. It exerts a drag on the Earth's rotation. It acts like a brake pad clamping down on the spinning planet. The result? The Earth is slowing down. It is imperceptible to us in our daily lives. But it is measurable. The day is getting longer. Every century, the length of the day increases by about 1.7 milliseconds. It sounds trivial. A blink of an eye is hundreds of times longer than that. But accumulate that blink over millions of years, and you change the definition of time itself. This is the trade-off. To push the moon away, Earth must sacrifice its speed. We are trading the length of our day for the distance of our satellite. It is a transfer of momentum from the spin of the planet to the orbit of the moon. This process is known as tidal friction, and it is relentlessly inefficient. Most of the energy generated by this tug-of-war is actually lost as heat. The sloshing of the water against the seabeds, the internal friction of the water molecules, the bending of the Earth's crust, all of this generates heat. In a sense, the moon's departure is warming the oceans, though by a microscopic amount compared to the sun. But the mechanical consequence remains. The Earth slows, and the moon flees. It's fascinating to realize that the map of our planet determines the speed of the moon's retreat. If the Earth were entirely covered in deep water, with no continents to get in the way, the tidal bulge would move relatively smoothly. But we have continents. We have shallow seas like the Bering Strait, the North Sea, and the Patagonian Shelf. These shallow waters act like breakwaters. They create massive turbulence and friction as the tides rush in and out. Scientists believe that right now, in our current geological era, the moon is drifting away faster than usual. We are living in a time of high resonant tides. The arrangement of our continents, North and South America stretching like a wall across the Western Hemisphere, blocks the flow of the tides, creating immense friction in the deep past, when the continents were clustered together in supercontinents like Pangaea or Rodinia. The ocean was one vast, open expanse. The friction might have been lower, the drift slower. But today, the continents are spread out, fighting the water, creating a powerful break. We are pushing the moon away at peak efficiency. Think of it like a figure skater spinning. When she extends her arms, she slows down. The Earth is trying to slow down, transferring its spin to the moon, which spirals outward like a weight held on a string. But unlike the skater who can pull her arms back in, we cannot reverse this process. The energy is gone, transferred to the dark vacuum of orbit. This mechanism also explains why we only see one face of the moon. Once, long ago, the moon also spun rapidly on its own axis. But the Earth, being much larger, raised massive tides on the moon, not of water but of solid rock. The Earth's gravity grabbed the moon's crust and braked its spin with brutal efficiency. Eventually, the moon slowed down so much that its rotation matched its orbit exactly. It became tidally locked. It spins exactly once for every time it circles the Earth. That is why we see the man in the moon. The Earth has already won the tug-of-war with the moon's rotation, freezing it in place. Now, the moon is trying to do the same to us. It is trying to slow the Earth down until we are tidally locked to it, until the Earth spins so slowly that one side of our planet constantly faces the moon, and the other side never sees it again. It is a long, slow battle for synchronization. The ocean is the rope in this tug-of-war, and every time the tide rolls in, crashing against the cliffs of Dover or the beaches of California, it is the sound of the Earth losing a fraction of its momentum, and the moon slipping 3.8 centimeters further into the void. Image of a diagram showing angular momentum transfer between Earth and moon, but this process hasn't been a straight line. If we calculate backward using the current rate of 3.8 centimeters a year, we run into a problem. The math suggests the moon would have been touching the Earth just 1.5 billion years ago. But we know the moon is 4.5 billion years old. The geology tells us the moon was there. So something must have changed. The break must have been eased at some point. The drift must have paused. To find the evidence of this paused departure, we have to look away from the water and towards the rocks. We have to read the diaries of the ancient mudflats, where the rhythm of the tides was written in stone billions of years ago. In the next chapter, we will uncover a time when the Earth stood still, or at least when its slowing stopped for 1 billion years. A lost era of stability that defies the simple math of the drift. Science is often about reading the archives that no one intended to write. When we want to know the history of the moon's drift, we can't rely on human records. We have only been writing for 5,000 years. To see the history of the moon, we must look at the tidal rhythmites. These are some of the most beautiful and poetic rocks on Earth. Imagine an ancient estuary, a shallow mudflat existing 600 million or 1 billion years ago. The tide comes in, depositing a fine layer of silt. The tide goes out, leaving the mud to dry. The next tide comes in, depositing another layer. Over eons, these layers are compressed into stone. When geologists cut into them today, they see a barcode of time. Thick layers for high tides, spring tides, thin layers for low tides, neap tides. By counting these layers, scientists can calculate exactly how many days were in a year and how many hours were in a day. At the moment that mud turned to stone. It is a fossil of a rhythm, a recording of the moon's heartbeat from the deep past. And when scientists analyze these rhythmites, they find something strange. We know that right now, the day is 24 hours long. We know that shortly after the moon formed, the day was perhaps 4 to 6 hours long. The logical assumption would be a steady, gradual slowing down, a straight line from 4 hours to 24. But the rocks tell a different story. They reveal that for a vast stretch of time, roughly from 1.8 billion years ago to 800 million years ago, the length of the day stopped changing, stalled. For nearly 1 billion years, the Earth's rotation settled at approximately 19 to 21 hours. Scientists call this period the boring billion. It's a somewhat unfair name given by geologists because, biologically and tectonically, things seemed relatively quiet. There were no massive glaciations, the oxygen levels were stable but low, and life remained mostly microscopic. But in terms of orbital mechanics, this era was anything but boring. It was a delicate cosmic balancing act. Why did the Earth stop slowing down? Why did the moon stop moving away significantly for 1 billion years? The answer lies in a battle between the moon and the sun. We've talked about the oceanic tide. The moon pulling on the water, creating friction that slows the Earth. That's the break. But there is another force at work, the thermal tide of the atmosphere. The sun heats the Earth's atmosphere on the day side. As the air warms, it expands and creates a bulge of high pressure. The sun's gravity pulls on this atmospheric bulge. But unlike the oceanic bulge, which drags behind the Earth's rotation and slows it down, the atmospheric bulge can actually push the Earth forward. Think of it as a solar engine trying to speed the Earth up, fighting against the lunar brake trying to slow it down. For most of Earth's history, the lunar brake, the ocean, has been much stronger than the solar engine, the atmosphere. That's why we've generally slowed down over time. But during the boring billion, a coincidence of physics occurred. The Earth's rotation was roughly 21 hours. At this specific rotation speed, the natural resonance of the atmosphere, the way it vibrates, like a bell being struck, synced up perfectly with the length of the day. This resonance amplified the sun's thermal tides. The solar push became massive. It became strong enough to cancel out the lunar pull. Imagine two giants arm wrestling. On one side, you have the moon using the oceans to drag the Earth back, trying to lengthen the day. On the other side, you have the sun using the resonance of the atmosphere to push the Earth forward, trying to shorten the day. For 1 billion years, they were deadlocked. The torque from the atmosphere canceled the torque from the oceans. The net result was zero. The Earth's rotation stabilized at roughly 19 to 21 hours. The day stopped getting longer. And because the Earth stopped slowing down, the transfer of energy to the moon paused. The moon stopped drifting away as quickly. It hung in the sky at a relatively constant distance, slightly closer than today, but stuck in a gravitational holding pattern. This stalled day might have had profound consequences for life. Biologists speculate that a 19-hour day was the rhythm that early eukaryotic life, the complex cells that would eventually become plants, animals, and us, adapted to. It was a period of stability that allowed the machinery of life to fine-tune itself before the next chaotic leap. But nothing lasts forever. The resonance eventually broke. Perhaps the atmosphere changed, cooling down or changing composition. Perhaps the continents shifted, changing the shape of the ocean basins and making the lunar tide stronger. Whatever the trigger, the deadlock was broken about 600 million years ago. The moon won. The oceanic break overpowered the solar engine. The Earth began to slow down again. The day began to lengthen from 21 hours to 22 to 23, and finally to the 24 hours we have now. The moon resumed its outward spiral, drifting further into the dark. This discovery fundamentally changes how we view the 3.8 centimeter drift. It is not a constant, steady, inevitable slide. It is a dynamic, lurching journey. The moon has sprinted away, then paused, then crawled, then sprinted again. We happen to live in a time when the drift is active again. The day is lengthening. The moon is leaving. The boring billion is long over, and the dynamic chaos of the Earth-Moon system is back in full swing. But the legacy of that time remains. It reminds us that our planet is a complex machine where the air, the water, the rock, and the sky all interact to set the clock. As we look at the moon tonight, we are seeing a traveler that once stopped to rest. But now it is moving again. And as it moves, it is slowly dismantling one of the most spectacular sights in the solar system. A sight that relies on a coincidence so precise, it defies belief. Image of a total solar eclipse showing the corona. In the next part, we will explore the cosmic coincidence. We will calculate the death date of the total solar eclipse. Because as the moon moves away, it gets smaller in our sky. And one day it will be too small to cover the sun. We are the privileged observers of a dying phenomenon. There are moments in nature so precise, so incredibly unlikely, that they feel less like physics and more like art. The most spectacular of these is the total solar eclipse. If you have ever stood in the path of totality, you know the feeling. The air grows cold. The birds stop singing. The sky turns a twilight purple. And then, in a single heartbeat, the sun disappears. In its place, a black hole hangs in the sky, surrounded by the gossamer white plumes of the corona, shimmering like a halo. It is a sight that has brought emperors to their knees and inspired myths across every culture on Earth. But this spectacle is a lie, or rather, It is a magnificent illusion born of a temporary cosmic coincidence. Consider the numbers. The Sun is a titan. It is 400 times wider than the Moon. It is a ball of fusion so massive it holds the entire solar system together. The Moon, by comparison, is a dusty rock, a mere quarter the size of Earth. Yet, in our sky, they appear to be almost exactly the same size. How? Because the Sun is also 400 times farther away from us than the Moon is 400 times larger. 400 times farther. The ratios cancel each other out perfectly. It is a geometry so exact that when the Moon passes in front of the Sun, it covers the dazzling face of the star, the photosphere, completely, but leaves the faint, delicate atmosphere of the corona visible. If the Moon were slightly smaller, the Sun's glare would blind us to the corona. If it were slightly larger, it would block the corona entirely. We live in the Goldilocks zone of eclipses. But this geometry is not permanent. It is a fleeting snapshot in a moving film. As the Moon drifts away at 3.8 centimeters per year, its apparent size in our sky is shrinking. It is becoming a smaller thumb trying to cover a distant street lamp. The math of the departure tells us exactly when this magic trick will end. Astronomers calculate that in approximately 600 million years, the Moon will have moved far enough away, about 23,000 kilometers farther than today, that its disk will be too small to ever cover the Sun completely. When that day comes, the era of the total solar eclipse will be over forever. Imagine the humans, or whatever post-human intelligence exists on Earth 600 million years from now. They will calculate the orbits. They will predict an eclipse. They will gather to watch. But when the Moon slides over the Sun, it will not blot it out. Instead, it will leave a blinding ring of sunlight around the edges, a ring of fire. This is known as an annular eclipse. We see them occasionally today when the Moon is at its farthest point in its orbit, apogee. But in the future, every eclipse will be annular. The sky will never go fully dark. The stars will never come out in the middle of the day. The corona, that ghostly crown of the Sun, will be lost to the glare, invisible to the naked eye from the surface of the Earth. The loss of totality is a loss of beauty, but it is also a marker of deep time. It tells us that we are privileged. We exist in a tiny, narrow window of Earth's history, a mere blink of 4.5 billion years, where this coincidence is possible. If we had evolved 500 million years earlier, the Moon would have been too big, blocking the corona. If we had evolved a billion years later, the Moon would be too small, leaving the Sun visible. We are here right now. We are the witnesses to the perfect eclipse. And the drift is already stealing it from us, second by second. In fact, we are already in the transition period. Today, Earth experiences a mix of total and annular eclipses. The balance is shifting. With every millennium that passes, the number of total eclipses decreases, and the number of annular eclipses rises. There is a profound melancholy in this realization. The universe is not static. The monuments of the sky are crumbling just as surely as the monuments of stone on Earth. The Moon is pulling away, and as it goes, it takes the shadow with it. But the end of eclipses is just a visual loss. The physical loss, the loss of the Moon's grip on our planet, carries consequences far more terrifying than a bright sky, because the Moon doesn't just block the Sun. It holds the Earth upright. Without its gravity, the Earth is a spinning top losing its momentum. And as any child knows, when a top slows down, it starts to wobble. In the next section, we will look at the invisible tether that keeps our seasons stable. We will look at Mars, a planet without a large moon, to see the chaos that awaits a world when its stabilizer leaves. The drift isn't just about distance, it's about balance. And the balance is tipping. Why do we have seasons? Why does the winter snow melt into spring flowers? Why does the summer heat inevitably give way to autumn leaves? It is because the Earth is tilted. As we orbit the Sun, our axis is not straight up and down. It is leaned over at an angle of roughly 23.5 degrees. This tilt, or obliquity, means that for half the year the northern hemisphere leans toward the Sun, bathing in direct light. For the other half, it leans away, plunging us into shorter days and cooler temperatures. This rhythm is the heartbeat of the biosphere. Triggers migration, hibernation, flowering, and mating. It drives the ocean currents and the global winds. But here is the question that should keep you awake at night. What keeps the Earth tilted at exactly 23.5 degrees? In the chaotic violence of the solar system, with massive planets like Jupiter and Saturn tugging on us from a distance, why hasn't Earth toppled over? Why hasn't the axis straightened up to 0 degrees, eliminating seasons entirely? Or worse, why hasn't it tipped over to 90 degrees, leaving the poles pointing directly at the Sun? The answer is the Moon. The Moon acts as a cosmic anchor. Its gravity reaches out and grabs the Earth's equatorial bulge, that slight spare tire of rock and water caused by our spin. By pulling on this bulge, the Moon exerts a stabilizing torque. It acts like the high speed of a gyroscope, resisting the tugs of other planets. It forces Earth to stay within a narrow range of tilt, wobbling only slightly between 22.1 and 24.5 degrees over cycles of 41,000 years. This slight wobble is known as the Milankovitch cycle, and even these tiny changes are enough to trigger ice ages. But thanks to the Moon, the wobble is contained. It is a gentle oscillation, not a catastrophic tumble. To understand what happens without this anchor, we only have to look at our neighbor, Mars. Mars has no large moon. It has two tiny, potato-shaped asteroids, Phobos and Deimos, but they are far too small to stabilize the planet. As a result, Mars is a victim of planetary chaos. Computer simulations show that over millions of years, Mars's axis swings wildly. It can stand straight up at 0 degrees, or it can tip over by as much as 60 or 80 degrees. Imagine if that happened on Earth. If Earth's tilt swung to 0 degrees, the seasons would vanish. The equator would burn under a permanent, unyielding sun, creating a band of uninhabitable desert. The poles would freeze into eternal darkness, locking up the world's water in ice caps miles thick. The temperate zones, where most of humanity lives, would disappear. Now, imagine the opposite. Imagine the Earth tipping over to 60 or 85 degrees, spinning on its side like Uranus. In this scenario, the North Pole would point directly at the Sun for months at a time. The Arctic would not be a frozen wasteland. It would be a boiling cauldron, with temperatures exceeding the hottest deserts of today. The ice would melt instantly, flooding the world. Meanwhile, the equator, currently the tropical heart of life, would be plunged into a twilight winter. Then, 6 months later, the situation would flip. The South Pole would bake, and the North would freeze. The entire planet would be subjected to climate whiplash so severe that complex forests and ecosystems could never adapt. Life might survive, but it would be a rugged, desperate existence, constantly migrating to escape the shifting zones of death. This is the chaotic obliquity that the moon prevents. But remember, the moon is drifting away. The anchor rope is getting longer. And as the distance increases, the torque, the stabilizing force, gets weaker. French astronomer Jacques Lasker performed famous calculations on this in 1993. He found that without the moon, Earth's tilt would be chaotic, varying between 0 and 85 degrees. But more recent studies have added a chilling nuance to this. They suggest that as the moon recedes, we are approaching a resonance crossing. There is a specific distance, a point in the future drift, where the moon's pull will become too weak to fight the gravitational resonance of Jupiter and Saturn. When we cross that line, the stability will shatter. The Earth's axis will begin to drift. It won't happen tomorrow. It won't happen in the next 1,000 years. But the geological record suggests that the stabilizing effect is already finite. We have perhaps 1.5 to 2 billion years of stability left. After that, the moon will be too far, a distant ghost that can no longer hold the Earth steady. The drift, then, is not just a goodbye. It is an unmooring. We are slowly becoming a lonely planet, vulnerable to the tug of the giants, destined to wobble in the darkness. But long before the axis tips and the ice caps melt, the life on Earth will feel the loss of the moon in a much more intimate way. It will be felt in the blood, in the genes, and in the rhythm of the reefs. In the next section, we will dive into the biology of the moon. We will explore how coral reefs, sea turtles, and perhaps even humans are tuned to a lunar clock that is slowly breaking down. When we look at the moon, we see a rock, a dead, gray world without air, without water, without life. It seems completely alien to the vibrant, breathing pulse of Earth. But this is a deception. In a very real sense, the biology of Earth is tethered to the geology of the moon. The connection is not just gravitational. It is genetic. For billions of years, life on Earth evolved in a bath of moonlight and tides. The first single-celled organisms in the primordial soup were pushed and pulled by the lunar rhythm. As life grew more complex, it didn't just ignore the moon. It internalized it. It built the moon into its very cells. This phenomenon is known as circulunar rhythm. We are all familiar with the circadian rhythm, the 24-hour internal clock that tells us when to sleep and when to wake, governed by the sun. But beneath that loud solar clock, there is a quieter, older lunar clock ticking away in thousands of species. Consider the Great Barrier Reef. For 364 days a year, the corals are individual colonies, fighting for space, filtering water, living their separate lives. But then, on a specific night in late spring or early summer, usually a few days after the full moon, something miraculous happens. As if obeying a silent command, billions of coral polyps across hundreds of miles of reef release their eggs and sperm into the water simultaneously. It is the greatest reproductive event on the planet. The ocean turns pink and cloudy with the sheer volume of gametes. It is a blizzard of life. How do they know? How does a polyp, an animal with no brain and no eyes, know the date? They taste the moon. Scientists have discovered that corals possess primitive light-sensing proteins called cryptochromes. These sensors are tuned not just to sunlight, but to the faint, specific spectrum of moonlight. They can detect the difference between a waxing gibbous and a full moon. When the light hits a certain intensity, it triggers a genetic cascade. The ancient clock strikes midnight. The release begins. This is not just poetry. It is survival. If the corals released their spawn randomly, the ocean currents would scatter them, and fertilization would never happen. They need a synchronization signal that reaches the entire ocean at once. The moon is that signal. But what happens as the moon drifts away? As the distance increases, the intensity of moonlight on Earth decreases. It is a slow dimming. Eventually, millions of years from now, the full moon will not be bright enough to trigger these ancient sensors. The signal will fade into the background noise of starlight and bioluminescence. The corals, if they still exist, will lose their conductor. Their reproductive sync will shatter. The blizzard of life will become a scattered drizzle, and the reefs may fall silent. It isn't just corals. Walk along the beaches of California during a full moon or a new moon in spring, and you might see the grunion run. Thousands of silver fish hurl themselves out of the water and onto the sand. They are surfing the highest tides of the month, the spring tides, to lay their eggs high up on the beach, safe from aquatic predators. They know exactly when the tide is highest. They rely on the moon's gravity to tell them when the window of opportunity is open. Or consider the chambered nautilus, a living fossil that has patrolled the deep oceans for 400 million years. Its shell grows in chambers, and looking at fossils, we can see that its growth rate is tied to the lunar cycle. The moon is etched into its armor. Even on land, the echoes remain. There is a long-standing scientific debate about the human menstrual cycle. The average cycle is roughly 28 to 29 days. The lunar cycle, the time from one full moon to the next, is 29.5 days. Is this a coincidence? Perhaps, but many evolutionary biologists argue that it is a relic, a leftover from a time when our ancestors, living in the tidal zones or primal forests, synchronized their reproduction with the brightest nights or the safest tides. We may have uncoupled from the moon in our modern cities, bathed in artificial light, but the shadow of the lunar clock may still be ticking in our physiology. The most profound impact of the drift, however, is not on individual species, but on the engine of evolution itself, the intertidal zone. This is the strip of land between the high tide mark and the low tide mark. It is a harsh, chaotic world. Twice a day, it is drowned in salt water. Twice a day, it is baked by the sun and dried by the wind. It is a place of stress. And in biology, stress is the mother of invention. It was in these tidal mudflats that life first learned to survive out of water. The first amphibians were likely driven by the tides, stranded in pools that dried up, forcing them to gulp air or drag themselves to the next puddle. The strong lunar tides of the past were the kick that pushed life onto land. As the moon drifts away, the tides are getting weaker. The amplitude, the difference between high and low tide, is shrinking. The intertidal zone is narrowing. The dynamic, chaotic laboratory where marine life learns to become terrestrial life is closing down. If we project this millions of years into the future, we see a biologically simpler world. A world with gentler tides, darker nights, and fewer evolutionary pressures driving the transition between sea and land. The moon's departure is slowly unplugging the biological clockwork of the planet. We are entering a time of biological arrhythmia. The signals are getting crossed. The triggers are failing. Life is resilient. It will adapt. It always does. But the romantic synchronicity, the idea that a rock in the sky tells a coral on the reef when to create life, is a phenomenon that is slowly, inevitably, fading into the dark. But if the biological silence is subtle, the physical silence will be deafening. As the moon leaves, it takes the speed of our world with it. The days are stretching, and in the future, a day on Earth will be a very different, very punishing experience. We take the 24-hour day for granted. It feels like a fundamental constant of the universe, like the speed of light or the force of gravity. We structure our entire existence around it. 8 hours of work, 8 hours of play, 8 hours of sleep. Our bodies, our economies, our power grids, everything is calibrated to this rhythm. But as we have learned, the 24-hour day is just a temporary stop on a sliding scale. The brake is still on. The moon is still stealing our angular momentum. The Earth is slowing down. Let's perform a thought experiment. Let's fast forward the clock, not by years, but by eons. Let's imagine an Earth where the drift has continued for another 1 billion or 2 billion years. The moon is a small, dim marble in the sky, and the Earth is tired. The rotation has slowed dramatically. A single day is no longer 24 hours. It is 30 hours, maybe 40, maybe even 60 hours long. What does it feel like to live on a planet with a 60-hour day? It would be a world of extremes. Imagine the sunrise. The sun comes up, but it moves agonizingly slowly across the sky. It hangs there, baking the land, for 30 straight hours. There is no relief. The afternoon heat builds and builds, far beyond anything we experience today. The ground cracks, the air shimmers, the photosynthesis of plants goes into overdrive and then shuts down as they exhaust their water reserves trying to survive the marathon of light. And then, finally, sunset comes. But the relief is short-lived, because the night is just as long. 30 hours of darkness. The temperature plummets. The land radiates all its heat away into the vacuum of space. The moisture in the air freezes. A deep, penetrating frost settles over continents that were baking just a day ago. This extreme diurnal cycle, hotter days, colder nights, would fundamentally change the weather. Our current weather is driven by the rotation of the Earth. The Coriolis effect is the invisible force that spins our hurricanes, drives our trade winds, and creates the jet streams that circle the globe. It is the spin of the planet that organizes the atmosphere into neat bands of climate. On a slow-spinning Earth, the Coriolis effect weakens. The jet streams would lose their coherence. Instead of fast-moving weather systems that bring rain and then clear skies, the atmosphere might stagnate. Massive, sluggish superstorms could form and sit over a continent for weeks at a time, unable to move. Rain would not fall in showers. It would fall in unending deluges. Droughts would not be seasons. They would be eras. The separation between the equator and the poles would change, too. Currently, the Earth's rapid spin bulges the atmosphere at the equator. As the spin slows, the atmosphere settles. The distinct climate zones, tropical, temperate, polar, might bleed into one another. The orderly circulation of heat from the hot equator to the cold poles would become sluggish and inefficient. And deep beneath our feet, another danger lurks. The Earth's magnetic field, the force field that protects us from cosmic radiation and solar wind, is generated by the geodynamo. This is the swirling of molten iron in the outer core. Scientists believe that the Earth's rotation helps to organize this swirling iron into a coherent field. It acts like the coil in an electric generator. If the Earth spins too slowly, does the dynamo fail? Mars, which spins at about the same rate as Earth today but has a much smaller core, lost its magnetic field billions of years ago. When the shield fell, the solar wind stripped away its atmosphere, turning a wet, blue world into a frozen red desert. If Earth's rotation slows significantly, our magnetic shield could weaken. The auroras, the northern lights, would drift down from the poles to the equator. But they wouldn't just be pretty lights anymore. They would be signs of a radiation bombardment. The atmosphere would begin to leak into space. The ozone layer would be shredded. The slow day is not just an inconvenience. It is an existential threat. Of course, this is the deep future. Humans, if we survive, might use technology to adapt. We might build domes or migrate with the twilight, constantly moving to stay in the comfortable zone between the burning day and the freezing night. We might become a nomadic species again, chasing the shadow of a slow sun. But the Earth itself will change. The shape of the planet will shift. Remember the equatorial bulge? The Earth is currently an oblate spheroid. It is fat around the middle because it spins. As it slows down, gravity will pull it back into a perfect sphere. This reshaping isn't gentle. It means earthquakes. It means the tectonic plates will have to readjust. The equator will shrink. The oceans will redistribute, flowing away from the equator and flooding the polar regions. The map of the world will be redrawn not by rising sea levels from climate change, but by the changing geometry of the sphere itself. The slowing spin is the Earth settling into old age. It is a loss of vitality, a loss of the dynamic energy that drives the winds and the currents. And all of this energy, the wind, the warmth, the magnetic shield, is being siphoned off drop by drop by the retreating moon. It is a high price to pay for a satellite, but is there a limit? Will the moon keep moving away forever until it breaks loose and wanders off into the solar system? Or is there a final destination? A point where the dance stops? The physics predicts a final, lonely embrace known as tidal locking. It is a state where the moon and the Earth face each other eternally, frozen in a stare. In the next part, we will look at this theoretical end of the line, a time when the moon will hang motionless in the sky over one half of the world and never be seen again by the other. If you could sit on a mountain peak and watch the Earth-Moon system for 50 billion years, assuming you were immortal and patient beyond measure, you would see the drift eventually come to a stop. The slow, grinding retreat of the moon is not an infinite journey. It has a destination, a final, frozen state where the dance ends and the dancers simply hold each other, motionless in the dark. This state is called mutual tidal locking. We are already halfway there. As we discussed earlier, the Earth has already won its battle against the moon's rotation. Eons ago, our gravity grabbed the moon and slowed its spin until it matched its orbit perfectly. That is why we only ever see one face of the moon. The man in the moon never turns his head. He is locked, staring at Earth forever. But gravity is a two-way street. The moon is doing the exact same thing to us. It is just taking longer because Earth is 81 times more massive than its satellite. But the brake is applied, and the wheel is slowing. In this distant, theoretical future, the Earth's rotation will slow down so much that it matches the moon's orbital period exactly. The day and the month will become the same length. Calculations suggest this final day-month would last about 47 of our current 24-hour days. Imagine what that world looks like. The Earth is no longer spinning rapidly beneath the moon. They are turning in perfect unison. This means the moon would stop rising and setting. It would simply hang in the sky, fixed at a single point, like a chandelier bolted to the ceiling of the heavens. If you lived in the hemisphere facing the moon, let's call it the lunar hemisphere, the moon would be a permanent fixture. It would go through its phases, new, waxing, full, waning, but it would never move across the sky. It would grow bright and dim, a pulsing ghost in the same spot, watching over the same ocean or the same continent for millions of years. But if you lived on the other side of the Earth, the dark hemisphere, you would never see the moon. Not once. You could live your entire life, generation after generation, without ever knowing that Earth had a companion. To see it, you would have to travel. You would have to take a pilgrimage across the globe, watching the moon slowly rise from the horizon as you traveled, until it hung high in the sky at the center of the lunar hemisphere. This creates a psychological and cultural split that is fascinating to imagine. The people of the dark hemisphere would have nights of uninterrupted, pristine darkness. Their astronomy would be unparalleled, with no moonlight to wash out the Milky Way. They would be the people of the stars. The people of the lunar hemisphere would never know true darkness. Even at night, when the sun is on the other side, the full moon would bathe their world in a light so bright it casts shadows. They would be the people of the moon, living under a constant, watchful in this locked state. The tides as we know them would vanish. The great lunar tides that rush in and out of our harbors today are caused by the Earth spinning underneath the moon. If the spin stops relative to the moon, the lunar tidal bulge freezes. The water would simply pool permanently on the side facing the moon and the side opposite it. The oceans would be still, disturbed only by the weaker thermal tides of the sun. The roar of the surf would be replaced by a silence that has not been heard since the oceans first formed. We actually have a model for this in our own solar system. Look at Pluto and its largest moon, Charon. They are roughly similar in size compared to Earth and the moon, and they are already mutually tidally locked. Charon hangs in Pluto's sky, unmoving. Pluto hangs in Charon's sky, unmoving. They pivot around a common center of gravity like two ice skaters holding hands. Spinning face dash to dash face. It is a profound intimacy, a cosmic stare down that lasts forever. However, getting to this state requires time, an immense amount of time. Current models suggest it would take about 50 billion years for the Earth to slow down enough to lock with the moon. And that is the tragic flaw in this story. The universe rarely grants that kind of time without interruption. 50 billion years is a number that belongs to the cosmos, not to a solar system. Our local neighborhood has a strict expiration date. Long before the Earth and moon can settle into this eternal, frozen embrace, a third player will enter the game and flip the board entirely. The sun is not watching this dance passively. It is evolving, and its evolution brings a new, violent force that threatens to undo everything the drift has achieved. The race is not just between the Earth's spin and the moon's orbit. It is a race against the death of a star. In the next chapter, we introduce the variable that changes everything: the red giant. The moon is trying to leave, but the sun is getting ready to swallow the sky. Throughout this journey, we have treated the sun as a steady, reliable source of gravity and light. It sits in the center of the solar system, keeping us warm, keeping us in orbit. But the sun is a ticking clock. It is a nuclear furnace consuming 600 million tons of hydrogen every second. And like any engine, eventually it will run out of fuel. When it does, roughly 5 billion years from now, it will not simply fade away. It will rage. As the hydrogen in the core is exhausted, the sun will begin to burn helium. The pressure will skyrocket. The outer layers of the star will balloon outward. The sun will transform from a yellow dwarf into a red giant. The scale of this expansion is horrifying. The sun will swallow Mercury. It will swallow Venus. Its atmosphere will expand out to roughly the current orbit of Earth. This transformation fundamentally alters the physics of the Earth-Moon system. The delicate 3.8 centimeter drift we have been tracking for eons will suddenly be overwhelmed by brutal new forces. First, there are the solar tides. Remember how the moon raises tides on Earth? The sun does too, but they are currently weaker because of the distance. As the red giant sun expands and its surface gets closer to Earth, its gravitational pull will become monstrous. The solar tides will begin to overpower the lunar tides. The Earth's rotation, which has been slowing down due to the moon, might be affected by this new solar grip. But the more immediate danger is atmospheric drag. The sun's outer atmosphere, the envelope of gas and plasma, is not a hard edge. It is a tenuous fog that gets thicker as you go deeper. As the sun expands, the Earth and the moon might find themselves orbiting inside the outer layers of the star. We would be plowing through thin solar gas. This creates friction, drag. Imagine running through water. It slows you down. Now imagine a planet and a moon running through the superheated gas of a dying star. This drag acts as a brake on the orbit itself. For the moon, this is a catastrophe. For billions of years, the moon has been using the Earth's rotational energy to push itself outward, spiraling away to safety. But the drag from the red giant's atmosphere acts in the opposite direction. It steals orbital energy. It pushes the moon inward. Astrophysicists have run simulations of this cosmic endgame, and the results are dramatic. It becomes a tug-of-war between two titanic forces. On one side, the tidal drift is still trying to push the moon away. On the other side, the solar drag is trying to pull the moon down. Who wins? Most current models suggest the sun wins. As the Earth spirals slowly into the sun's atmosphere, the moon's orbit will begin to decay. The drift will reverse. After billions of years of moving away, the moon will stop, hesitate, and then begin a slow, terrifying spiral back toward Earth. It will get closer and closer and closer. It will grow in the sky, transforming from the small, distant marble of the future back into the terrifying giant of the Hadean Eon. But this time, there is no magma ocean to push it back. This time, the drag is relentless. Eventually, the moon will reach a point of no return known as the Roche limit. This is the invisible line around a planet where the gravity holding a moon together is weaker than the tidal forces trying to rip it apart. It is roughly 18,000 kilometers from Earth. If the moon spirals inside this limit, it will not collide with Earth as a solid object. Instead, it will shatter. The gravity of Earth will grab the near side of the moon and pull it harder than the far side. The stress will crack the lunar crust. Mountains will crumble. The moon will be stretched into an egg shape, then a cigar shape, and then, in a silent, apocalyptic moment, it will disintegrate. The moon will vanish. In its place, Earth will gain a ring, a spectacular, bright ring of debris, moon rocks, dust, and boulders will encircle the Earth. We will look like Saturn, but our ring will be made of the corpse of our oldest companion. This ring will cast a shadow over the equator, blocking the angry red light of the dying sun. It will rain meteors down on the atmosphere for millions of years. This is the likely fate of the drift. It is not an eternal separation. It is a boomerang journey. The moon leaves only to be forced back by the death of the sun, ultimately sacrificing itself to become a tombstone ring around a dying world. It is a violent, poetic end to a partnership that defined 4.5 billion years of history. But let's step back from this fiery cliff. Let's zoom out, because this drama, the drift, the locking, the destruction is not unique to us. Across the galaxy, countless other moons are dancing with their planets. Some are drifting away. Some are falling in. The next part, we will look at the wandering moons of our solar system. We will compare our moon to Triton, which is doomed to fall, and Phobos, which is living on borrowed time. We will see that drifting away is actually a privilege. It is the hallmark of a stable, mature system. The moon is leaving, yes, but in the grand context of the cosmos, leaving is the only way to survive, at least for a while. In our journey so far, we have looked at the drift of our moon with a sense of melancholy. Feels like a loss, a slow abandonment. We see the moon receding into the darkness, and we feel a pang of loneliness on behalf of the Earth. But if we widen our view, if we step back and look at the other relationships in our solar system, we realize something startling. The drift is a luxury. The drift is a sign of a relationship that has worked. Because for many other moons in our neighborhood, the story does not end with a long, slow goodbye. It ends with a scream. To understand how lucky we are, we have to travel to the outer edges of the solar system, to the ice giant Neptune. Circling this blue, windswept world is a moon named Triton. It is a strange, frozen place, spewing geysers of nitrogen into a thin atmosphere. But the most unusual thing about Triton is not its geology. It is its direction. Triton orbits Neptune in retrograde. That means it circles the planet in the opposite direction to Neptune's own rotation. If you were floating above Neptune's north pole, you would see the planet spinning counterclockwise, while Triton stubbornly marches clockwise. This backward motion tells astronomers a violent backstory. Triton was not born there. It was likely a dwarf planet from the Kuiper Belt, a cousin of Pluto, that wandered too close and was captured by Neptune's gravity billions of years ago. It is an adopted child, forced into an unnatural path. And because of this retrograde orbit, the tidal mechanics we discussed earlier work in reverse. Remember the oceanic break on Earth? Earth spins faster than the moon orbits, so the tidal bulge drags the moon forward, boosting it higher. On Neptune, the situation is inverted. Because Triton is moving against the planet's spin, the tidal bulge it raises on Neptune acts like a drag chute. Pulls against Triton's motion. It steals energy from the moon's orbit. The result is that Triton is not drifting away. It is spiraling in. Every year, Triton gets a little closer to Neptune. It is a slow death spiral that has been going on for billions of years. And the end is inevitable. In a few billion years, Triton will cross the Roche limit of Neptune. The planet's gravity will overpower the moon's internal structure. Triton will be ripped apart, shattered into billions of icy shards. Neptune will gain a magnificent, bright ring system, perhaps rivaling Saturn's, but it will come at the cost of its greatest moon. Now, let's come closer to home. Let's look at Mars. Mars has two small moons, Phobos and Deimos. Deimos is far enough away that it is slowly drifting outward, much like our moon. But Phobos, Phobos is in trouble. Phobos is tiny, a lumpy, cratered rock that looks more like an asteroid than a moon. But its problem is speed.
Phobos orbits mas incredibly fast.
It is so close to the surface, only about 6,000 kilometers up, that it zips around the planet 3 times every single day. This creates a fatal geometry. Because Phobos is orbiting faster than Mars is spinning, the tidal bulge it raises on the red planet doesn't lead the moon. It trails behind it. The bulge drags backward on Phobos. Gravity is reeling it in. Phobos is falling toward Mars at a rate of about 1.8 centimeters per year. It is a slow-motion crash that has been happening since the solar system was young. For any future Martian colonists, Phobos will be a source of anxiety. It is getting bigger in the sky. In about 30 to 50 million years, a blink of an eye in geological time, Phobos will meet its end. It will either crash into the Martian surface, creating a massive scar, or, more likely, it will be torn apart by tidal forces before it hits, turning into a ring of dust that will rain down on the equator for millennia. Compare these fates to our own. Triton is doomed by its backward rebellion. Phobos is doomed by its frantic speed. But the Earth and the Moon? We are in the Goldilocks zone of orbital mechanics. Our Moon orbits in the same direction as Earth spins, prograde. This avoids the Triton trap. And our Moon orbits slower than the Earth spins. This avoids the Phobos trap. Because the Earth spins faster than the Moon flies, we transfer energy outward. We push our partner away rather than pulling it down. It is a gentle, repulsive force, a gravitational cushion that ensures the Moon will never crash into us, unless the red giant sun interferes, as we saw. This outward drift is actually a safety feature. It clears the space around the planet. It ensures stability. It means that for 4.5 billion years, life on Earth has not had to worry about the sky falling. We have had a steady, albeit retreating, light in the night. When astronomers look for exoplanets, planets orbiting other stars, and wonder which ones might host life, this moon stability is a key factor. If a planet has a moon that spirals in quickly, the resulting crash could sterilize the world. If a planet has no moon, the axis might wobble chaotically like Mars. We need a moon that stays but not too close. We need a moon that leaves but not too fast. The 3.8 centimeter drift is the price we pay for safety. It is the cost of having a long-term relationship in a universe that prefers collisions. So, the next time you feel sad that the moon is leaving, remember Phobos. Remember Triton. To drift apart is better than to crash together. The long goodbye is a privilege. It means we have had time. Time for oceans to settle. Time for the axis to stabilize. Time for life to crawl out of the mud and look up. But while the cosmos takes the long view, we humans live in the short term. And in our short-term world of seconds, minutes, and hours, the drifting moon is causing a very different kind of problem. It is breaking our clocks. In the next part, we leave the orbits of Neptune and Mars and come down to a laboratory in Boulder, Colorado. We will look at the conflict between the perfect, rigid time of our machines and the messy, slowing time of our planet. The moon is making the Earth late, and our technology doesn't know how to handle it. We live in a world governed by precision. Your GPS navigates you to within a few meters. The internet trades stocks in microseconds. Power grids synchronize electricity across continents at the speed of light. All of this depends on one fundamental assumption: that we know exactly what time it is. For thousands of years, the definition of time was simple. One day was one rotation of the Earth. Noon was when the sun was highest. A second was just a tiny fraction, 1/86th 400th of that rotation. The Earth was the clock. But in the mid-20th century, we broke that bond. We invented something better than the Earth. The atomic clock. In laboratories around the world, scientists began measuring time not by the spin of a massive, sloshing planet, but by the vibration of a single atom, specifically the cesium-133 atom. When hit with energy, this atom oscillates, it ticks, exactly 9,192,631,770 times per second. This number never changes. It doesn't care about tides. It doesn't care about the moon. It doesn't care about magma or wind. It is a constant of the universe. In 1967, humanity officially redefined the second. It was no longer a slice of the Earth's day. It was 9 billion ticks of a cesium atom. We had created atomic time, TAI. It is perfect. It is relentless. It marches forward in a straight, unbending line. But the Earth does not march. It dances. And as we have learned, because of the moon's drift, the Earth is dancing slower and slower. This created a crisis. We had two times. Atomic time, which is perfect, and astronomical time, UT1, which is based on the actual rotation of the Earth, and they were drifting apart. Because the moon is stealing Earth's energy, the Earth's rotation is slowing. The Earth second is getting tiny bit longer than the atomic second. There's a difference of milliseconds per day, but it adds up. If we ignored it, eventually atomic noon would happen at sunrise. The clock on your wall would say 12 p.m., but the sun would be setting. We would lose the connection between the clock and the sky. To fix this, the Keepers of Time, the International Earth Rotation and Reference System Service (IERS), invented a band-aid, the leap second. Since 1972, every few years we have had to pause atomic time. We wait for the tired, slowing Earth to catch up. Usually on June 30th or December 31st, at midnight, the clocks do something strange. They tick from 23 hours 59 minutes and 59 seconds to 23 hours 59 minutes and 60 seconds, and then to 00:00:00. That extra second, that 60th second, is a monument to the moon. It is a second of silence in our digital world, inserted to pay the debt of the lunar drift. But this solution is becoming a nightmare. For computers, a leap second is chaos. Software is designed to count forward, never to repeat or pause. When a leap second is added, Linux servers crash. Airline reservation systems freeze. Financial markets glitch. In 2012, a leap second caused outages at Reddit, Yelp, and LinkedIn, and grounded flights in Australia. Tech giants like Google and Meta hate the leap second. They have invented smearing, where they smudge that extra second across a whole day, making every second a tiny fraction longer, just to avoid the crash. They are literally bending time to hide the Earth's deceleration. And the debate is raging right now. Should we abolish the leap second? Should we let Earth drift away from atomic time? If we do, in a few thousand years, our clocks will be out of sync with the sun by an hour. In tens of thousands of years, noon will be at midnight. We would sever the link between human time and nature's time forever. This technical squabble is actually a profound philosophical conflict. It is a clash between the rigid, linear order of human technology and the organic, decaying rhythm of the cosmos. We want the universe to be a machine. We want the day to be exactly 86,400 seconds. But the moon says no. The moon says, the day is what I say it is. The drift of 3.8 centimeters is not just moving a rock in the sky. It is stretching the fabric of our days. As the moon moves further away, the Earth slows more. The gap between atomic time and Earth time will widen. In the distant future, we won't need a leap second every few years. We might need one every month. Then every week. We are trying to build a civilization on a foundation that is moving. We are trying to measure a song that is slowing down. The leap second is our humble admission that we are not in control. No matter how precise our lasers, no matter how perfect our atoms, we are still riding a spinning rock that is subject to the drag of the tide. We are still at the mercy of the departure. So, the next time you see a clock tick, remember that it is lying to you. It is pretending that seconds are all the same. But the Earth knows better. The moon knows better. Time is stretching, pulled taut by the gravity of a leaving friend. But what if we didn't have to wait millions of years? What if the connection broke tomorrow? What if, through some impossible cosmic magic, the moon simply vanished? In the penultimate part of our journey, we will conduct the ultimate thought experiment. We will wake up to a world without a moon.
No tides. No stavelause.
No light in the dark. It is a scenario that reveals just how deeply we are entwined with our satellite. Throughout this journey, we have talked about the moon leaving us slowly, a millimeter here, a centimeter there, over timelines that defy human comprehension. But sometimes the best way to understand the value of something is not to watch it fade, but to imagine it gone entirely. Let us perform the ultimate thought experiment. Let us snap our fingers and erase the moon. Imagine that tonight, at exactly midnight, the satellite that has accompanied Earth for 4.5 billion years simply vanishes. No explosion, no debris, just sudden, absolute absence. The first thing you would notice is the light. If you were standing outside on a night that should have been a full moon, the world would plunge into a darkness you have likely never experienced. We are used to the moon acting as a natural lantern, reflecting the sun's light back to us, illuminating forests, roads, and oceans. Without it, the night becomes an abyss. The stars would blaze with a brilliance we rarely see, but the ground beneath your feet would be pitch black. For humans, this is disorienting. For the animal kingdom, it is catastrophic. Predators that rely on moonlight to hunt, owls, wolves, big cats, would suddenly find themselves blind. Prey animals, conversely, might find a sudden, confusing safety in the shadows. The entire balance of the nocturnal ecosystem, honed over millions of years of lunar cycles, would be thrown into chaos. Migratory birds, which use the moon and the polarized light it creates to navigate, would circle in confusion, lost in the dark sky. Sea turtles, waiting for the bright night to hatch and scurry to the ocean, would wait in vain or march toward the artificial lights of cities, doomed. But the real shock would come the next morning. At the ocean's edge, without the moon's gravity, the oceanic break we discussed would disappear instantly. The massive tidal bulges that travel around the globe would collapse. Now, the tides wouldn't vanish completely. The sun still exerts a gravitational pull on our waters. But the solar tides are only about 40% as strong as the lunar tides. The great, heaving rhythm of the ocean would turn into a gentle, shallow pulse. Surfers would wake up to flat seas. Harbors that rely on high tides to bring in large ships would find themselves permanently shallow. The intertidal zones, those rich strips of life between high and low water, would shrink drastically. Billions of creatures, from mussels to crabs to small fish, would die as their habitat dried up or became permanently submerged. The smell of decay would waft from the coastlines of every continent. The ocean currents, driven in part by tidal mixing, would slow down. This would stagnate the flow of nutrients from the deep sea to the surface. The plankton blooms that feed the whales and produce half our oxygen might wither. The ocean would grow quieter, stiller, and far less alive. Then, there is the rotation. With the moon gone, the brake is off. The Earth would stop slowing down. The length of the day would stabilize immediately. We would be stuck with our current 24-hour day forever, or until the sun's effects took over. In a sense, we would gain a kind of eternal consistency, but at the cost of our planetary partner. But the most terrifying consequence would play out over the long term. Remember the stabilizer? Without the moon to anchor our axial tilt, the Earth would be at the mercy of Jupiter and the other planets. The wobble would begin. It wouldn't happen overnight. It would be a slow, drunken stumble over millions of years. The axis would drift. The North Pole might wander down toward the equator. The Sahara Desert might freeze under a polar night. The Amazon rainforest could be scorched by a relentless, unmoving summer sun. The predictable, nurturing seasons that allowed agriculture and civilization to flourish would be replaced by a chaotic climate roulette. Life on Earth is resilient, but few things could survive a world where the equator becomes the pole and the pole becomes the equator every few million years. We would become a world like Mars, scarred, shifting, and hostile. This thought experiment reveals a profound truth. The moon is not an accessory. It is a vital organ of the planetary system. It is the counterweight that keeps the machine running smooth. When we look at the drift, that 3.8 centimeters a year, we are seeing the slow loosening of these bolts. We are seeing the gradual onset of this moonless world. We are millions of years away from the worst of it, but the process is the same. To lose the moon is to lose the rhythm of the tides, the light of the night, and the stability of the seasons. It makes you look at that white cratered rock differently, doesn't it? It's not just a decoration, it's a lifeline. And yet, despite all this importance, despite the violence of its birth and the vital role it plays, the story remains the same. It is leaving, and we have to accept that. In the final part of our journey, we will synthesize everything we have learned. We will stand at the end of the pier and wave goodbye, because the story of the moon is ultimately a story about the beauty of temporary things. We began this story in the desert of West Texas, watching a laser beam shoot into the sky to measure a distance that changes by the width of a fingernail every year. We traveled back to a time of fire, when a giant, red moon loomed over a magma ocean. We stood in the mudflats of the boring billion, where the day stalled. We watched the sun disappear in total eclipses that will one day be impossible. And we peered into a future where the Earth slows, the moon freezes, or perhaps, in a fiery twist, returns to shatter into a ring. Through all of these eras, one theme resonates. The Earth-Moon system is not a statue. It is a process. We humans have a deep desire for permanence. We build stone cathedrals. We write laws. We carve our names into trees. We want to believe that the world we were born into is the world that will always be. We look at the moon and think, there it is, eternal, unchanging. But the 3.8 centimeters tell us the truth. Stability is an illusion created by the shortness of our lives. If we could see time as the rocks see it, we would see the moon spiraling out like a stone on a string. We would see the days stretching. We would see the tides calming. This realization that our closest companion is drifting away could be a source of sadness. It feels like a cosmic abandonment, a slow breaking of a bond that has defined our planet since its infancy. But there is another way to look at it. The drift teaches us to value the now. We are living in the golden age of the Earth-Moon relationship. Think about the coincidences. We are alive at the exact moment in history when the moon is the perfect distance to create total solar eclipses. We are alive when the tides are strong enough to drive ocean currents, but not so strong that they destroy our coasts. We are alive when the axis is stable, giving us the predictable seasons that allowed us to invent farming, writing, and science. We are the beneficiaries of a specific, fleeting arrangement of gravity. We stand in the sweet spot between the violent closeness of the past and the lonely distance of the future. The long goodbye is not a tragedy. It is a natural evolution. The universe is defined by motion. Galaxies flee from each other. Stars burn through their fuel. Planets migrate. Moons drift. To expect the moon to stay put is to deny the fundamental nature of the cosmos. The moon has done its job. Kick-started our chemistry in the tidal pools. It stabilized our chaotic youth. It slowed our frantic spin to a livable rhythm. And now, like a parent who has raised a child, it is slowly stepping back. It is giving the Earth space. It will take billions of years for the final act to play out. Long before the moon breaks free or falls back, humanity will have evolved into something else, or vanished, or moved to the stars ourselves. We will not be here to see the end of the story, but we are here to see the middle. We are here to measure the drift. We are here to look up and understand that the silent, silver face watching us is not a fixture, but a traveler. So, the next time you find yourself under a clear night sky, take a moment to look at the moon. Really look at it. Don't just see a flat white disk. See the heavy, cratered sphere hanging in the dark. Feel the invisible tether of gravity connecting it to the water in your cells and the tides in the sea. And then acknowledge the motion. Visualize that imperceptible 3.8 centimeters. Whisper a quiet thank you to our drifting partner. Thank it for the seasons. Thank it for the tides. Thank it for the stable days. And then let it go. Because in this vast, restless universe, nothing stays forever. And the beauty of the moon is not that it is permanent, but that for this brief, shining moment in eternity, we are traveling together. Thank you for joining me on this journey through deep time and gravity. It is a pleasure to share these moments of wonder with you. If you enjoyed this drift through the mysteries of our solar system, please consider liking this video and subscribing to Mysteries Beneath Earth. Your support helps us keep exploring the strange, quiet stories that lie hidden in the data. Until next time, keep looking up and sleep well.